In this lecture, we'll discuss the concept of cardinality. This is a topic that at first seems rather simple, but actually ends up becoming one of the most subtle and probably interesting topics in all of mathematics. And that's when we go from finite to infinite sets. So let's actually just recall what we already know. So let's suppose we have a finite set. So let A be a finite set. Really going to emphasize the finite part. Then the cardinality of A. Cardinality of A denoted. Remember how we denote cardinalities with these absolute value bars. So cardinality of A is how we read that. Is simply the number of elements of A. So it's defined to be the number of elements of the set A. Okay. So example, if we have a set little a, little b, little c, well, that has cardinality 3. Cardinality of A is 3. You just count them. Okay, so that's all there is to it, it seems. But there are actually some rather interesting properties of cardinality when we combine this, the idea of cardinality with functions. So suppose I have a function. Suppose I have a function. But yeah, we're sticking with finite sets. So f from A to B, and yeah, say they're both finite sets. Got to always emphasize that. It's basically everything I'm going to say is not true for infinite sets. And suppose that let's start with this. So suppose the cardinality of A is strictly greater than the cardinality of B. So A has more elements than B. And the question is, can f, this function f, be bijective? Called bijective means both injective and surjective. Okay. Well, you might feel like the answer is no. But let's draw a picture here. So let's say we have A and B. So A is a larger set. So let's say A has 3 elements and B has 2 elements. Well, here's A, here's B. And let's try to draw a function. So we need to start with everything in A and go somewhere. So go there, and then we can send this one there. And all of a sudden we have an element where, we can't really send this to either of these, right? So let's put a question mark. We can't really send that to either of these. Why? Because then the function would fail to be injective. We'll have a 2-to-1 mapping there. So yeah, the answer is no. And why is it? It's because f will fail to be injective. F will fail to be injective. There will be 2 elements of A that have to map to the same element of B. And in fact, this has a special name. It's called the pigeonhole principle. So the name comes from the idea that, in this picture, suppose we have 3 pigeons and 2 pigeonholes. And each of the pigeons is going to go into a pigeonhole. Well, what's the conclusion? Well, it's not possible, but let's say all the pigeons have to go somewhere. Well, there's going to be a pigeonhole that has 2 or more pigeons in it. That'll be the conclusion. That's what the pigeonhole principle says. It's essentially the statement, the function from a set with a strictly larger cardinality to another set with a strictly smaller one cannot be injective. Okay, so hopefully that's pretty intuitive. What about the opposite? So what if instead we had the cardinality of A is smaller than the cardinality of B? What can we say about that kind of function? So let's again draw a picture here. but we're going to make A have the 2 elements and B have the 3 elements. Here's A, here's B, and let's create a function. So we need everything in A to go somewhere, so that'll go there, and then this has to go somewhere. Let's send it there, and again we see a problem, right? So what goes to this one? Well, it appears nothing can go there. So yeah, again, you cannot have a bijection. So yeah, again, the answer is no. In this case, what's the problem? Well, there's sort of too many elements of B. There'll be at least one element that's missed entirely. So in other words, F will fail to be surjective. Okay. So it looks like the only chance of creating a bijection between 2 finite sets is if their cardinalities are exactly equal. And in fact, there's a theorem. There's an even better theorem. The theorem actually says it. These are equivalent in some sense. So let's let A and B be finite sets. Always want to emphasize the finite part. This theorem is absolutely not true if they are infinite sets. So we're going to start with finite sets. But that's what we're going to segue into after this. We're going to start looking at some infinite sets. So let A and B be finite sets. Then, here's the statement. There is a bijection. So there exists some bijection. A bijective function from A to B if and only if, so double arrow like this, if and only if their cardinalities are equal. Okay? And I'm not saying that every function from A to B has to be a bijection. Of course not. You can map everything in A to the same element of B. But I'm just saying there exists a bijection. Okay? And these two are completely equivalent. Okay? And so what's the forward direction? Well, we essentially walked through the counterpositive of that. So if these cardinalities are different, then it's going to fail to be either injective or surjective. Okay? That's the forward direction. How do you prove the reverse direction? Well, if the sets are the same cardinality, we have to construct a bijection. But you can probably imagine how you might do that. So just pair up an element of A with an element of B. And now, just look at the remainder of both sets. You now have one fewer element than before, but still the 2 cardinalities of those sets are going to be equal. So you can essentially prove it by induction. You can construct a bijection that way. So these are equivalent statements. But this, I want to emphasize this, finite sets. Let's now look at some sets that are not finite. So this is going to be a new section here. So what about infinite sets? This is where it gets really interesting. What about infinite sets? So consider the sets. Let's take A to B, I don't know, the integers. That's a good infinite set. And B to be the even integers. Sometimes that's denoted 2z. But yeah, what I mean by 2z, I mean the even integers. Okay. I want to ask you a question. So question. Which is bigger? If any. Okay. All right. Well, if you're like me, I had sort of an immediate answer to this question. My immediate answer, and this will be maybe argument 1. My first answer is obviously z is bigger. Because this is all the integers and this is just the even ones. So yeah, z the integers are the bigger set. So z is bigger. Why? Because well, every even integer is an integer, but not every integer is an even integer. So this one contains things that this one does not. Okay, But this one's entirely contained in that one. So it's because 2z is, the even integers are a subset of the integers. But the integers are not a subset of the even integers. There are more integers than even integers. Okay, so this is not, let me cross that out, subset of 2z. Okay. That's a perfectly good argument. If you think about this a little longer, though, you might come up with a different kind of argument. You could also argue that they're exactly the same size. And here's why. I'm not saying this is a more valid argument than the first one, but yeah, they're exactly the same size because so I mean, you could say they're both infinite, so their size is both infinity. That's a little bit of a cop-out. I want to give you an even more convincing argument. So because, for all we know, there might be infinities that are bigger than other infinities. But here's my argument. So we can actually put the elements of both sets in bijection. So we can put the elements in one-to-one correspondence. In one-to-one correspondence. Here's what I mean. Let's take the integers. 0, 1, 2, 3, 4, etc. -1, -2, -3, -4, etc. Right? And then let's take the even integers. So what do we have? 0, 2, 4, 6, 8, -2, -4. I'm not drawing this in a very descriptive way here, but here's what I mean. So the 0 we can pair up with the 0. The 1 I'll pair up with the 2. The 2 I'll pair up with the 4. I'm essentially pairing every integer with its double. And you'll see if I do that, I have created a perfect one-to-one mapping between the integers and the even integers. It's a bijection, in fact. Right? It is a bijection. And in fact, I can tell you a formula for it. So the function, what's the formula? This is one where you don't have to think too hard. So the function from z to 2z given by f of x is 2 times x is a bijection. Let's quickly prove that it's a bijection. So how do we prove something is a bijection, a bijective function? We have to prove that it's injective and surjective. So to prove it's injective, what do? We start by taking two elements. So for x1 and x2, we look at f of x1 and f of x2. So here's what we're assuming. We're assuming that f of x1 is equal to f of x2. So 2x1 is equal to 2x2. And we want to show that x1 equals x2. But that's clear here, right? I just divide by 2. And I get x1 equals x2. So that just proves it's injective. How do we prove it's surjective? Well, we take an element over here which has the form 2x, and we need to find an x that maps to 2x. Right? We need to show there exists something over here that maps to the element 2x. But that element is just x, right? X is going to go to 2x. So this is f of x. Okay, and that's my element. So yeah, this is definitely injective and surjective. We can see that in the picture too, so it is kind of overkill. But yes, hopefully I've convinced you this is a bijection, and because of that, I claim they have the same size. Why? Because even though it seems like the integers have more elements, for every single integer, I can pair it up with an even integer. Okay? So there can't be any more integers than even integers by that argument. So again, that's very convincing, I think. But the first one's also convincing. So you might have a preference for which of these arguments you prefer. But in fact, I mean, one is not true and the other one is false. It's not like that. The problem is just this question doesn't really mean anything, because what do we mean by bigger, right? We need to be more precise. So in other words, we need to define cardinality, some idea of cardinality or size of infinite sets, and that's what we're going to do next. Okay, and we're actually going to take this second argument as inspiration. And in fact, this theorem is going to be our ultimate inspiration, because we want our definition to also work for finite sets. So we are going to say, here's a definition, very important definition. We say sets A and B, not necessarily finite. We say that they have the same cardinality. The same cardinality if there's a bijection between the two. If there exists a bijection between the two. Okay. Bijection from A to B. By the way, if I had said B to A, like technically this is the definition A to B, but if I had said B to A, that would also be correct, because if there's a bijection from A to B, there must be a bijection B to A, and that's because f would be invertible in that case. The inverse function will be the bijection. We denote this by saying cardinality of A equals the cardinality of B. But this does not mean count elements of A. If this is an infinite set, especially, it does not mean that. This means, this notation here, this whole phrase here means this. There exists a bijection from A to B. Okay? So when you see something like this, you should be thinking, there is a function going from A to B that is a bijection. And that's really what this means. Okay. So that's an important definition there. Let's do some examples. So, I mean, what's the first example? The first example is Z and 2Z have the same cardinality under this definition, right? So that resolves this argument here. At least under this definition, right, of cardinality, and this is a standard definition. So these have the same cardinality. Okay, and we can write this. We can write the cardinality of Z is the same as the cardinality of 2Z, meaning there's a bijection from Z to 2Z. In fact, there's an explicit formula for one. Let's do another example. So let's do an example where we have, we'll also do infinite sets. So let's do the interval. 0 to 1, including the endpoints, and the interval 2 to 5. And both of these I'm thinking of as intervals of real numbers. So these are in the real numbers. Okay. So just every number between 0 and 1, inclusive of the endpoints. So every number between 2 and 5. Well, do these have the same cardinality? Seems like that one is 3 times longer than that one. So seems like it should have 3 times as many numbers. But is there a bijection between the two? Yes, there is. Right. So we'll define a function from, let's call this one A and this one B. So simplify the notation. And let's see if we can come up with one. So I need to send this whole interval into that whole interval. How do we do that? Let's first multiply every number here by 3, and then we've created the interval from 0 to 3. So I'm going to do what? F of x is 3x, and then I need to add 2 in order to turn the interval from 0 to 3 into the interval from 2 to 5. So there's my bijection. And again, why is this injective? It's injective because if we had 3x plus 1 equaling, 3x1 plus 2 equaling 3x2 plus 2, does that imply that x1 equals x2? Yes, absolutely. You just minus 2 and then divide by 3. So that implies these are equal. In fact, any linear function like that is going to be injective. Well, so long as that coefficient is not 0. But then it wouldn't be linear. So, okay, and then is it surjective? This is a little more interesting. So let's do, so that's injective. So surjective. How do we do that? We'll let y be something in we'll let y be in the set B. Okay. And can we get to y by choosing some x? So in other words, can we get 3x plus 2 to equal y? Can we find an x in there? Well, let's just try solving for that x. So this is a typical idea. Okay, so what happens if we solve for x? We get 3x equals y minus 2. So x would have to be y minus 2 over 3. So the claim is this number is the one that if I plug it in, I will get to y. And one thing we have to be a little careful about, is this number really in this interval? Right? Is that number in that interval? Well, y is in this interval. So the smallest y can be is 2, and that would correspond to x equals 0. The largest y can be is 5. 5 minus 2 is 3. 3 over 3 is 1. That would correspond to x equals 1. So yes, indeed, this x is always going to be in the interval 0 to 1. It will be between 0 and 1. Yes, so these have the same cardinality. Okay. Let's do another example. So what if we have 0 to 1, let's say the open interval, and let's do a surprising one actually. 1 to infinity, so like literally every real number greater than 1. Is there a bijection here? Yes, in fact there is. I mean, there are many, but here's one. You have to think of a function that maps that to that in an injective and surjective way. So f is going to be the function 1 over x. That works, right? So 1 over x will take a number between 0 and 1, and it'll turn into a number between 1 and infinity. This will be the reciprocal. And yes, you can check that's a bijection. I won't do that. By the way, so I'm doing too many examples here. I guess you can never do too many examples. 0, 1, and what if I had 0 to infinity? Just make it even a little more extreme. Can you do that? Well, yeah, you just do that, right? You just do that, and then you minus 1. So that'll just be 1 over x minus 1. So these have the same cardinality as well. Okay. Let's do a tricky example now. This is a tricky but important one. So we're going to let a be the natural numbers and b be the integers. Okay. Is there a bijection there? So the answer is yes. Here's how it works. Or here's how it could work. So let's take all of our natural numbers there, and we're going to try to map these to the integers. We have to hit every integer, though. So I'll draw the integers over here. Minus 2, minus 3. Just keep going, right? Okay, so here's my natural numbers. Here's my integers over here. Here's my natural numbers. Can we create a function from here to here? It'll hit everything? Yes. So here's one way to do it. Send 1 to 0. I can send 2 to 1. And here's what I don't want to do. I don't want to send 3 to 2, 4 to 3, etc. Like, I don't want to keep going in that fashion, because then that'll never hit these, right? So I want to immediately start alternating. Send 3 to minus 1. I'll send 4 to 2. I'll send 5 to minus 2. I'll send 6 to 3. I'll send 7 to minus 3. Hopefully this picture convinces you can continue in this fashion. This will be a bijection, right? You don't even need a formula for it. This is a function, right? It's a function that does this. By the way, here's my attempt at coming up with a formula for this. So if you really want one, negative 1 to the n times 2n. Let's see, is it minus 1 or plus 1? I think minus 1. Then plus 1 over 4. So if I did that right, that formula should map these to these, and it should hit everything. So there's an explicit formula. We don't even need that though, right? Not every function needs to have a formula. So what's the conclusion here? Actually, these two sets have the same cardinality. There are just as many natural numbers in some sense as there are integers. You can create a bijection between the two. Okay, let's do one last example. There's another really important one. This example will be the natural numbers and this is an even more surprising one. Pairs of natural numbers. All ordered pairs. That's what n cross n is, right? All ordered pairs of natural numbers. So here's what I mean. You have like 1 and 1. Here, let me do it like this. 2, 3, 4, 5, etc. So take either one of these to be your natural numbers. I just want to draw out all the pairs. So I have 1, 1. I'm going to draw out elements in B. So you have 1, 1, is an element. Let's see, 1, 2 is another element. 1, 3, 1, 4. They sort of naturally fit in this two-dimensional array or grid. So 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. We have 3, 1. I'll stop at some point, but yeah, you get the idea. So I'm drawing out this set n cross n. You might say, well, how? And this keeps going, right? So all possible pairs 4, 1, 4, 2. Okay, I'll stop. 5. You get the idea. And it keeps going, right? So can I find a bijection between just the natural numbers themselves, like one list of numbers, and this entire grid of pairs of natural numbers? That seems quite surprising that should exist. So maybe these do not have the same cardinality. But in fact, they do have the same cardinality. And there's some quite clever ways you can write a bijection between the two. So here's the first one I usually think of. So this one, I'm going to go in a reverse order. So I'm going to go from there to there. But again, if I have a bijection from there to there, I can have one from there to there. It's just going to be the inverse function. Because a function is invertible, the inverse function exists if and only if it's bijective. So you can go either way. Here's going to be my function. I'm going to map the pair A, B to 2 to the A minus 1, my exponent, times 2B minus 1. Let's see, how did I come up with this? So what is this doing here? Well, it's taking a pair and it's sending it to a natural number. And so the A, like let's say this is the A here, that's just going to control what power of 2 my natural number has. Notice that this factor here is odd. So it's just going to control in the factorization, the prime factorization of my natural number, what should the power of 2 be? So anything in the sixth row, I'm going to map to 2 to the 6. I'm going to map to 2 to the 5. Anything in the first row, I'm just going to, there isn't going to be a power of 2. So my odd numbers, these are going to go to my odd numbers. And then in the second one, I'm just going to map to the odd number 2b minus 1. So anything in column 1 is going to go to 1. Anything in column 2 is going to go to 3. Anything here is going to go to 5, 7, etc. And I claim I can hit any natural number that way. Right? Because any natural number is going to have a power of 2. And a power of 2, it might be no power of 2, right? It might just be 2 to the 0, but that's included here. And then it's going to have some other part of its factorization, some odd primes, and this goes to all the odd numbers. So I'm going to hit every natural number. And furthermore, 2 of these are not going to coincide. So if I start with different values of A and B, I'm never going to get the same number. And the reason is essentially because of unique factorization. So every number has a unique prime factorization. So the power of 2 has to be the same if I factor it as a product of primes. And I'll force the A's to be the same. And then that forces the second factor to be the same also, because these are different numbers for different b. So this really is a bijection. So actually these two, so yeah, this is a bijection. So actually n cross n, the cardinality of n cross n is the same as the cardinality of just the natural numbers. Very surprisingly, I would say. And by the way, there's another way to do this. So this is the more common way. You start by sending, so I want to send this to number 1, and then, so I'll go to number 1, and then this one will go to number 2, then 3, so I'm sort of going down the diagonals, and this will go to 4, 5, 6, 7, 8, 9, 10. It is fun to try to come up with a formula for this. This will go to 11, 12, so see, I'm sending that to 2, I'm sending that to 3, that to 4, that to 5, that to 6. It is possible to come up with a formula for this, although it's not important. This picture alone should convince you that this is going to be a way to map this whole grid onto just the natural one copy of the natural numbers. Okay, it's going to hit everything in the grid, right? And again, I'm not saying go down the whole first column. I'll never get to the end. That's why I'm doing these sort of shallow diagonals this way. So this is a common trick. This is another kind of function that shows that these two are bijective. Great. Okay, so that is an introduction to this concept of cardinality. Thanks for watching.